Hello friends, this is Gangadhar from Maths Ganga. See, in our channel we are just giving top 10 conceptual ideas related to different concepts, related to different topics of mathematics for your JEE mains, right? Already few chapters are completed and you are all learning through those top 10 conceptual ideas, and now in this class I am going to handle 3D geometry, which is very scoring concept of JEE mains, and for sure you will get one questions and sometimes you may get two questions also in JEE mains from this 3D geometry. If you analyze, if you learn these 10 conceptual ideas, easily you will score, you attempt those questions from JEE mains, right? And among my 10 ideas, 10 conceptual ideas from 3D geometry regarding JEE mains, this is the first one. Just have a look. In first one, just I am introducing you, just I am revising everything related to the three-dimensional system, right? So in three-dimensional geometry, we will analyze a space. In this 3D, as we have a plane in 2D, we have space in 3D. In two-dimensional geometry, we divide the total plane into 4 parts called as quadrants. Here in 3D, we divide a space into 8 parts and each part is mentioned as an octant. And these 8 octants are just separated by 3 planes and then 3 axes and then origin. So the planes are xy plane, yz plane, zx plane, whereas the axes are x, y and z axis and origin, right? Then a point pxyz of the space, if you have a point pxyz of the space, here this x coordinate, y coordinate and z coordinate just represents the distances from O to P along the axis. Distances from O to P along the axis, okay? Distance of the point P from origin along x-axis is the x coordinate. In same way, along y coordinate is y-axis is y coordinate, and along the z-axis is the z coordinate. And if you take a point in the space, it is of the format xyz, and a general point on the plane. If you take any general point on the axis, on x-axis the coordinates are a 0 0. X coordinate is a and the coordinates of yz are 0 0. And any general point on y-axis is of the format 0 b 0. Any general point on z-axis is of the format 0 0 c. Similarly, if you go for a general point on the planes, xy plane, z coordinate is 0, yz plane, just look there here, yeah, and then yz plane, x coordinate is 0, I will take 0 bc, and then on zx plane, y coordinate is 0, a 0 c, and a point in the space, okay, not on the axis, not on the planes, any point in the space. If you take a point in the space and the coordinates of that point are a, b, c, right? Just like xyz, I took here like a, b, c. And now I have a point xyz in the space, and I need to calculate the distance of the point from the axis, from the planes and from the origin. Those distances, right? Distance of the point pxyz from planes, xy plane it is mod z, yz plane it is mod x, zx plane it is modulus of y. Whereas the distance of the point from the axis, from x-axis, the distance is root x square plus y square, root y square plus z square. Distance of the point from x-axis, from x-axis it is root y square plus z square. From y-axis it is what? Root x square plus z square. And the distance of the point from the z-axis it is root x square plus y square. In the same way, the distance of the point xyz from the origin is given by root x square plus y square plus z square. So this is all about the first conceptual idea of the formula and the midpoint. As we know, the distance and section region formulas in 2D, we need to extend it for the third coordinate in 3D. So the distance between 2 points A, B is given by the rule that square root of x2 minus x1 whole square plus y2 minus y1 whole square plus z2 minus z1 whole square. Whereas coming to the section division formula. Section division formula in the sense, if these 2 points are on a line segment, you may say line segment AB, then there is a point P which is dividing this line segment AB in the ratio m is to n, then the coordinates of the point P will represented by this section division formula. That P is just simply mx2 plus nx1 by m plus n, mx2 plus nx1 by m plus n, comma my2 plus ny1 divided by m plus n, comma mz2 plus nz1 divided by m plus n. What it is? It's section division formula. That in the sense, point P which is dividing the given points A, B in m is to n ratio. If that m and n is equals to 1, this section division formula will become a midpoint, and the midpoint formula is just simply x1 plus x2 by 2, comma y1 plus y2 by 2, comma z1 plus z2 by 2. We know all these formulas related to the two-dimensional system. You just extend it for the third coordinate, and these are the formulas in 3D, right? This is all simply the first point related to the three-dimensional system. Okay, right? So you must have some idea related to these points of the first conceptual idea to answer many questions, right? And then have a look. I will come up with the second conceptual idea. Now, the second conceptual idea related to the three-dimensional geometry, and this idea explains us about the direction angles, direction cosines, and the direction ratios, right? See, in two-dimensional geometry, to describe the direction of a line, we need slope of that line. We generate that slope with respect to the inclination of the line, where the inclination is the angle made by the line with x-axis. You just leave there. And now coming to three-dimensional geometry, direction of a line is described by 3 angles, and those 3 angles are, you may say them as alpha, beta, gamma. We call them as direction angles. Here this alpha, beta, gamma are the angles made by any line of the space with the axis respectively. Alpha is the angle made by the line with x-axis, beta is the angle made by the line with y-axis, and gamma is the angle made by the line with z-axis. These 3 angles usually describes the direction of the line. Okay, always in measuring these angles and analyzing these angles is somewhat bit difficult, and that's why based on these direction angles we will generate direction cosines. See, if you have direction angles, then cos alpha, cos beta, cos gamma are mentioned as direction cosines, real numbers corresponding to those 3 angles, and these direction cosines are usually denoted by LMN. Okay, in generally we take direction cosines of a line as LMN. And then direction ratios. Direction ratios are generally represented by ABC, and these ABC are in ratio of L is to M is to N. Okay, and in relation to the direction cosines, we have one logic here. See, if LMN are the direction cosines, and for sure these direction cosines will satisfy one particular rule, that L square plus M square plus N square is equals to 1. At the end, once again, direction of a line is described by 3 angles, alpha, beta, gamma. We'll call them as direction angles, and those angles are the angles made by the line with the coordinate axis. See, if alpha, beta, gamma are the direction angles, then their cosines are mentioned as the direction cosines, and we usually represent the direction cosines as LMN. And always that L square plus M square plus N square is equals to 1. We need to memorize it. And after that, in ratio to this LMN, if you consider any set of numbers, those numbers are mentioned as direction ratios. Direction ratios are 3 numbers, usually A, B, C, which are in same ratio as LMN. Okay, any set of numbers which are in same ratio as L is to M is to LMN are mentioned as direction ratios. And now, if we have DCs of a line LMN and DRs of a line ABC. First, suppose if I have DCs LMN, then to get DRs of that line, I have DCs and I need to write DRs of that line. So for that, you just multiply these DC's element with any constant k as you wish. Okay, the constant may be fraction also. So if you have DC's, you just multiply with a constant, they will generate DRs. And if you have DRs ABC, then to generate DC's, then to write DC's, you just divide these DRs ABC, you need to divide with the root of a square plus b square plus c square. So DC's to DRs, multiply with any constant. DRs to DC's, you just divide with root of a square plus b square. So that's the conversion from DC's to DRs. And another way of conversion is, I have 2 points on the line. If I have 2 points on the line, then the DRs of that line are generated by x2 minus x1, y2 minus y1, z2 minus z1. So I have 2 points on the line. So if you just observe x2 minus x1, y2 minus y1 and z2 minus z1, these three represents the DRs of the line. Okay, so 2 points to DRs to DC's, we usually convert like that. Okay, and I have two lines L1 and L2. Line 1, the DRs are A1, B1, C1. Line 2, DRs are A2, B2, C2. Here theta is the angle between those two lines. Then cos theta is given by the rule that A1, A2 plus, B1, B2 plus, C1, C2 divided by the root of A1 square plus, B1 square plus, C1 square into root of A2 square plus, B2 square plus, C2 square. Direction ratios, direction cosines, direction angles, all these are just for lines. Okay, usually we use direction ratios to generate different formulae. So if direction ratios of two lines are A1, B1, C1 and A2, B2, C2 and theta is the angle between those two lines, then cos theta is given by this particular rule. And from this rule it is very clear that if L1 is perpendicular to L2, then what will happen? If L1 is perpendicular to L2, then theta will become 90, cos 90 is 0, and that's why this numerator, what it is? A1, A2 plus, B1, B2 plus, C1, C2 is equals to 0. If two lines are perpendicular and the DRs of those two lines are A1, A2, A1, B1, C1, A2, B2, C2, then we have this particular logic. As well as if the two lines are parallel, if L1 is parallel to L2, having these DRs, then it is very clear that they are in the same direction. So the ratio between their DRs also will become same. A1 by A2 is equals to B1 by B2 is equals to C1 by C2. So this is the second conceptual idea of the three-dimensional geometry, which completely describes about DC's DRs and the conversion from DC's to DRs. Okay, so this analysis of DC's and DRs is very helpful in analyzing different forms of the planes and different forms of the lines, everything which we come in the next points. Just have a look.